this lecture, we will first consider combination of two mirrors. So, we in a way have considered this earlier, but we had considered two mirrors at perpendicular to each other. But now, today we will just look at how we can combine these two mirrors at some other angle. So, let us say I have one mirror which is basically in the xz plane, and another mirror intersecting the first mirror at the origin, and it makes, let us say, an angle of alpha. Call this mirror as mirror M2, and we want to find out what is the resulting operation when sigma 1 reflection operation is followed by sigma 2 reflection operation. So, we want to find out the resulting symmetry. Now, in the last lecture, I had constructed a reflection matrix for the mirror M2 and as well as mirror M1. So, for the mirror M2, the reflection matrix is cos 2 alpha sin 2 alpha 0 sin 2 alpha minus cos 2 alpha 0, and the last row is 0 0 1. For the mirror M1, the reflection operation sigma 1 that we have also done 1 0 0 0 minus 1 0 0 0 1. So, sigma 1 is the mirror in the xz plane with the normal to the y axis. So, therefore, the second row of the second matrix has a minus 1 and other on the diagonal, while the other two remain 1. Now, when I multiply these two matrices, one would get the following resulting matrix: cos 2 alpha, so first row into the first column, then first row into the second column would give me minus sin 2 alpha 0. Now, the second row into the first column would give me sin 2 alpha cos 2 alpha 0 and then 0 0 1. Now, let us see what kind of a matrix is this. If I compare from a previous lecture, this was, one can look at this particular matrix cos theta minus sin theta 0 sin theta cos theta 0 0 0 1. Now, this is a rotation matrix and the rotation axis itself is on the z axis. So, coming back to this, if I compare the two matrices, so my rotation matrix, let me just quickly write this down: rz theta. So, if I rotate through an angle of theta around the z axis, the matrix is cos theta minus sin theta 0 sin theta cos theta 0 0 0 1. And if we compare these two matrices, instead of theta in this matrix, basically we have 2 alpha, which means that we actually have rotation of around the z axis through an angle 2 alpha. So, which means that out here at this origin here, we have basically a rotation of A 2 alpha. So, the resulting operation that we get is A 2 alpha. Now, this was the matrix method of working this out. We can also visualize this thing geometrically. So, let us start with the same kind of diagram again. Put the two mirrors, one in the xz plane, other at an angle of alpha. So, this is M1, M2, and let us see how we can work this out geometrically. So, let us say that I put a asymmetric motif. Let me put this motif here. And just identify one point of this motif, and let us say the angle that is made between this point and the origin, let us say this angle is beta. Now, mirror M1 will reflect this motif and change its handedness to this location. So, if I call this as motif number 1 and let us say this is right handed, then this becomes motif number 2, which is left handed, and clearly this angle would also be beta. So, this is the first operation of reflection sigma 1. Now, the second operation, which would be sigma 2, would reflect motif number 2 through the mirror M2 to somewhere out here, with the again the handedness changes and the handedness would be like this, which means this is, let us say, motif number 3 and it becomes right handed. So, the question that we can ask is that how do I go from 1 to 3? Now, it is clear that handedness of 1 as well as the handedness of 3 is a right handed, and therefore, a rotation operation should be there. So, 1 to 3 would be through a rotation. Now, we have to find out what is the angle through which we need to rotate. So, let us work out a little bit more. So, I have this angle is beta. So, what would be this angle? The angle made by motif number 2 and the mirror M2, which would be clearly would be alpha minus beta. Now, motif 2 reflects through mirror M2 and therefore, this angle should also be alpha minus beta. So, what is the total angle of rotation? So, total angle of rotation that is required would simply be just add up all of these. So, I have beta, I have another beta, then I have alpha minus beta plus another alpha minus beta. This would be the total angle, and if we see this, all the betas will cancel out and we are left with 2 alpha. So, again I have the same result as we got from the matrix method, and therefore, I have a rotation of A 2 alpha at the origin. Now, let us move a bit further, that can we have any arbitrary value of alpha? or will there be some restrictions? Because remember, we are talking about rotation, and therefore, if there has to be a rotational symmetry which is crystallographic, then we need to put some restrictions on alpha, and let us find out what those restrictions are. Therefore, not all values of alpha would be allowed. And the reason is that only crystallographic rotations allowed. So, if there has to be, and let us say rotation axis A, let us say 2 pi upon n for an n-fold rotation matrix, then n is restricted to 1, 2, 3, 4 and 6. So, very clearly n into 2 alpha has to be necessarily be equal to 2 pi, which means that alpha would be equal to pi upon n. So, this is where the restriction on alpha will come, the angle between the two mirrors. Let us write down all the restrictions, or let us write down all the allowed values of alpha. So, 1, 2, 3, 4 and 6. So, for n is equal to 1, it is simply pi. What does this mean? Basically, it means that M1 and M2 are in the same plane, essentially only a single mirror is there. For n is equal to 2, I will have pi upon 2, then pi upon 3 for n is equal to 3, pi upon 4 for n is equal to 4 and pi upon 6. So, I have 180 degrees, 90 degrees, 120, 60 degrees, 45 degrees and so on, and 30 degrees. So, if let me just put down 180 degrees, 90 degrees, then I have 60 degrees, 45 degrees and 30 degrees. These are all the angles that are possible for the two mirrors M1 and M2. And this particular result we have already seen when we added a two-fold rotational symmetry and a mirror, then a new mirror got created at 90 degrees. Or conversely, we can say if I put two mirrors M1 and M2 at 90 degrees to each other, I had a two-fold rotational symmetry that would be present at the intersection, and that is by n is equal to 2. So, let me write another thing. Conversely, in a more general way, that if there is a mirror or reflection operation sigma 1 followed by A alpha, a rotation of alpha, the resulting operation would be, and I can show this through again through a matrix. So, I have cos alpha minus sin alpha 0, sin alpha cos alpha 0 and 0 0 1. So, let me just also show this, that I am putting the mirror M1 here, and I am putting a two-fold rotational symmetry as shown in the figure. Now, one could easily work this out, that through matrices, that the angle for the mirror that I will get would be alpha upon 2. So, there would be a reflection operation sigma 2 at an angle of alpha 2. So, one can show this on a diagram. So, I have a mirror M1, then I will have a mirror M2 at an angle of alpha by 2, where the rotational when is A alpha. So, now this is I think should be quite straightforward, and we are now coming close to getting all the possible two-dimensional point groups. But just before that, let me just put on a couple of properties of rotation and reflection matrices. One of them being, so I have, let us say, a rotation matrix A alpha, then the determinant of A alpha will always be plus 1, and basically we are assuming that this is a right-handed coordinate system, and that is what we have been using all along. Another is that the inverse of the matrix A alpha is equal to the transpose of the matrix A alpha. What this basically means is, then A alpha inverse multiplying into A alpha is equal to A alpha transpose multiplying into A alpha, which is equal to the identity matrix. Now, for the reflection matrix, the determinant of a reflection matrix will always be minus 1, and the reflection matrix would be its own inverse, which means the inverse of the reflection matrix sigma is equal to sigma itself. Again, all this means is that sigma inverse multiplying into sigma is the identity matrix. So, this was just an aside to know a couple of properties of these matrices. Now, let us develop all the possible two-dimensional point groups very quickly. But I think what I will do is we will develop all the two-dimensional point groups starting in the next lecture.